All right, our final talk before break is by Connor, and we're moving from pike to trout. Sorry, Connor Reeve.
Yeah, from pike to trout, but still keeping with hypoxia, kind of. Okay, so my name is Connor Reeve. I'm a postdoctoral research associate with Cornell and the Adirondack Fisheries Research Program. Today I'm going to be talking about some of the work we've been doing on brook trout. So brook trout can be described as a cold-adapted, oxygen-loving fish species. And although these adaptations are traits that help them proliferate in the cold Northeast, these traits are starting to become maladaptive given climate trajectories. As we know, it's warming, and this isn't good for this sensitive fish species. This also isn't great considering the fact that we know that native brook trout populations aren't thriving. This synthesis from 2008 did a great job of showing this, demonstrating that roughly 70% of native brook trout populations have already been significantly reduced or extirpated altogether. Fortunately, the work that we do is in the Adirondacks, so up here where we've got bits of green still existing, which is good. And in fact, the brook trout that we work on are lake dwelling. So you might think, these lake dwelling brook trout, they're buffered from warming, right? They've got all that access to cold, deep water down, below that warm surface layer. But as was shown by a previous Adirondack Fisheries Research postdoc, Dr. Stephen Jane, these critical cold water refuges are becoming more and more hypoxic. And this is because of increased dissolved organic carbon loading, brownification, and prolonged stratification. So for extended periods during the summer, these lake-dwelling brook trout aren't just experiencing warming at the surface, they're also experiencing increasingly hypoxic bottom water conditions, resulting in this oxythermal compression or these periods of oxythermal squeezes where a lot of the suitable habitat is compressed to just this small area. And so Steve did a really great job showing that this is a big problem throughout the Adirondacks, but we still don't really know what the fish is doing themselves. And that's where I come in. So I wanted to determine how are these oxythermal squeeze periods impacting brook trout in the Adirondacks. So the first thing I wanted to do, though, is to determine what are the conditions that these brook trout can tolerate. And to do that, I subjected them to a series of temperature and oxygen stress tests. For the temperature stress tests, I put them in these little containers, and I warmed them up at about a degree a day. And during that warming, I assessed various behaviors. I looked at how their feeding changed, how their spontaneous activity changed, how their sheltering responses changed, and ultimately I recorded the temperatures at which they lost equilibrium or died. For the hypoxia or oxygen stress tests, I first had to run a series of respirametric analyses to determine what are the routine costs of activity, what are the routine costs that these fish need to sustain themselves. And then afterwards, I could subject them to declining oxygen conditions and determine at what point is their routine metabolism constrained by oxygen. And this is a really good indicator of hypoxia tolerance in fish. So here are the results from the temperature stress tests. Shown here on the left is their feeding responses with warming. And we can see that just above 21 degrees Celsius, we see a steep decline in their feeding. Similarly, at around the same temperature as well, we saw a decline in sheltering behavior. We also saw a small change in their activity as well, although this was somewhat limited given the small confined space that they had. So this is a good indicator that there's an important sublethal threshold at 21 degrees Celsius. And we also found that around 23 degrees and up to about 26 degrees, 28 for some of the more tolerant fish, this is when a loss of equilibrium or mortality begins to occur. So we can use these as our sort of sublethal and lethal temperature thresholds for our brook trout. These are the results from the oxygen stress tests. Without getting into too much detail, we found that generally at concentrations a little less than 3.5 milligrams is when their routine metabolism was limited. There was again some variation based on temperature and strain, but the takeaway here is roughly at about 3.5 milligrams per liter they can tolerate these conditions. Okay, the next was using this criterion, we wanted to see how are these fish actually behaving in oxythermally stressful environments? And we did this by using acoustic telemetry and a series of study lakes. And we had these pretty nifty tags that transmit both depth and temperature, so we could determine where the fish are, what the temperatures they were experiencing. And we also had strings of temperature and dissolved oxygen loggers in the lake, which allow us to predict the conditions that they were experiencing. And so here's, shown on the left here is depth measurements from a series of fish in one of our study lakes. And we can see they sort of go, deeper in the middle of the summer and then back shallower. But I think this trend makes a lot more sense when we overlay the oxythermal criteria informed by our lab estimates. So shown here in blue is the suitable habitat, red is unsuitable, and orange is stressful. And boy, what do you know, it looks like they're in that suitable band for a lot of the summer. And this is pretty well the same for the rest of our study lakes. We had 6 in total, shown here are 4, but generally what you can see is that they're tracking this blue suitable band of habitat. But this is very qualitative. We can obviously take statistical methods and answer various questions using the data that we've gathered here. The first thing I wanted to do was double check my lab-based estimates, make sure what I did was correct. So shown here are cumulative distribution functions with this red line indicating the proportion of observations at or below a given temperature. The black line is what we predict the threshold to be based on the lab-based estimates, and the blue line is what the sort of fish are showing us that are swimming in the wild. And so you probably can't see black or blue here because I got it bang on. It seemed that exactly the fish in the wild were avoiding temperatures greater than 21 degrees Celsius. And here, maybe I was a little bit liberal in my estimate of 3.5 milligrams per liter. But we look at this on a lake-by-lake basis. We can see that some of this data is skewed by the more oxic lakes, and that when we look at the sort of hypoxic lakes, again, my estimates were pretty bang on, so I can sort of pat myself on the back for doing good lab work. We can also look at their oxythermal preference, and we can find that typically they like to occupy waters at around 12 degrees, a little less than, and oxygen concentrations at about 7 or 8 milligrams per liter. And notably, these are pretty cold and high temperature and oxygen preferences. The literature sort of suggests that brook trout will occupy or prefer waters between 12 and 16 and oxygen between 6 and 8. So there's a real sort of trend for cooler and more oxygen or oxygenated water for these fish. And this really sharp peak maybe implies that the fish themselves are actually seeking out optimal oxygen conditions more so than they're seeking out optimal temperature conditions. And I have a few hypotheses as to why this is the case. This is kind of right around the oxygen that they need to maintain maximal performance. So this kind of makes sense, but often we don't think about oxygen selection in sort of fish physiology or ecology. We think about temperature selection. So in any case, this is a pretty neat result in my mind. We can also look at how their behavior changes with respect to oxythermal compression. So shown here are the, the outputs from a series of generalized additive mixed models, basically showing seasonal trends in various behavioral metrics. This top metric, sorry for the people in the back, shows vertical velocity. This middle metric is directional changes, so this is effectively significant up and down movements. I could explain to you how I calculated that later, but this is a good indicator of sort of foraging activities. And then this bottom metric is the delta temperature. So this is the difference between the internal body temperature as measured by the acoustic tags and the temperature and the ambient temperature as predicted by our temperature loggers that are in the lake. And so what we can see is that, vertical velocities decrease a little bit. There's a huge drop in these, I'll sort of call them foraging-related behaviors in the middle of the summer. And we generally see a greater difference between their internal and ambient temperatures, typically being much lower than we predict in the middle of the summer. But what's great about these additive mixed models is that we can add linear predictors to better understand how things like oxythermal metrics are influencing behavior. And we can pull those out of the generalized additive mixed models to get relationships like this that control for differences between lakes and seasonalities and get a better understanding of how things like the minimum and maximum suitable depth. This is effectively how deep is that warm layer penetrating into the water, and how shallow is that hypoxic layer going up into the water column, as well as the totable suitable habitat. So imagine, that blue zone in the middle again. How are these things actually influencing these behaviors? And I'm not going to explain each and every one of these. They're all highly significant, but the takeaways are that declining oxythermal habitat constrains depth use significantly. It limits foraging-related behaviors, and it encourages thermal refuge use. So, taken together, we know that they're being compressed into a small area. It appears to be limiting foraging use. That, these sort of things where you can have confinement stress, it can cause mortality. It's not a great thing for fish. And we also have this other axis that we're seeing after the squeeze. So, shown here is data from one of our more stressful lakes, with this pink band representing significant periods of oxythermal squeezes. And this first panel on the left shows their internal temperature, the middle one, their depth profile. And basically, after the compression lifts, we see these fish moving very shallow and getting quite warm. Now, this isn't up to those sort of sublethal temperatures that I mentioned earlier, but these are definitely suboptimal temperatures. Brook trout don't want to be here if they can help it. So what we're taking this as, especially because we don't see this in our less stressful lakes, is this is evidence of their foraging being impaired during the compression, and then once they can access the more profitable littoral resources, they're shooting up there to get whatever energy they can to recoup lost energy reserves. So all this together, this isn't looking great for the brook trout. And in fact, we can see that high temperature and low oxygen increases mortality risk. In some of our more stressful lakes, we can infer mortality by the lack of detections or the absence of movements. And we can see, it's kind of hard to see back there, but some of these cross hatches, and these all indicate mortality events that we detected in our acoustically tagged fish. And we can actually quantify this as well using a survival analysis. There it goes. And basically, this indicates that for every meter decrease in suitable oxythermal habitat, this equates to a 2.25 increase risk of mortality for these fish. So this is significant, and unfortunately, this appears to be occurring across the Adirondacks. Fortunately, one of the things that I didn't mention here is that all of this work has an additional axis in that we're trying to assess strain resilience throughout all of this. And so we're seeing differences in their thermal tolerance, their hypoxia tolerance, their behavior across all these metrics that I just shown. We're also looking at things like growth and survival rates. And ultimately, we're hoping to identify strains that are more tolerant to hopefully negate some of this, these negative environmental changes on the population. I obviously don't have time to get into all this, but if you find this stuff interesting, find me later. I'd love to chat about it. But with that, I'd like to thank you all for listening and take any questions if there's time.
We do have time for questions. Yes?
So I see that you're going to be looking into strains, and so I had the question of, the lakes that you looked at, were they ever stocked, or are they fully wild?
They're pretty well all stocked. There's some, so we did compare, well, I'll say pseudo-wild fish, because they have been stocked before, to those that we have stocked. But a lot of this work is a big sort of climate adaptive stocking project and understanding how these different stocked fish are responding to these changes. Essentially, we want to improve stocking and recruitment success by selecting those that are more tolerant.
Yes.
Connor, how do you distinguish this compensatory feeding after compression from seasonal movements into shallower waters after they cool?
Yeah, so we only see that abrupt movement into shallow waters, and they're still very hot waters for the record, only in the stressful lakes and only after that period of compression. So we don't have, an exactly hard science on this, but observationally, this is what we're sort of taking it to indicate.
Yeah.
Are you determining resilience for the different strains the way you did it in the lab prior, or do you have a different method to do that?
We're doing multiple, so it's a multi-pronged approach. So, like, yes, we can say that this strain is more temperature tolerant or hypoxia tolerant, but that, that means something to me as a lab physiologist, but as a field ecologist, I also want to know how are they responding in the field. There could be differences that can, knock that off. Like, one of the strains may be really temperature tolerant, but more bold, and things like this. So, we're trying to, answer your question to multiple approaches. Yeah.
Other questions? Yes.
Sure. Do you see like a relationship between the squeeze effect, like these interesting behavioral patterns and growth? Like, does the growth back up the stressful period and things of that nature?
We're getting inklings of that now, but this next summer is our big. It's sort of the 5th year of our program, and so we've got tons of marked and recaptured fish, and so hopefully I'll have a more concrete answer for that soon.
So for some of the more stressful lakes, do you have any idea of a prognosis of the point at which the temperature and oxygen level might be just not favorable to any kind of strain of brook trout?
Yeah, so in one of those lakes that I did show there, all of our acoustically tagged fish died. So probably close to that, but I think that there's probably other factors that are at play. I mean, we know that the amount of rain in a given season can influence groundwater inputs and things like this. So I think that there's a bit of interplay, but that lake was very stressful. Something I'd like to do is determine the amount of time fish can go in a significantly squeezed or a complete loss of suitable habitat using sort of like bioenergetic analyses and things like this. But some of the smaller, shallower, more hypoxic lakes, yeah, they're having a hard time.
Other questions? We do have a little time. Yes.
Are there any non-constrained lakes in the study, lakes that aren't squeezed, where you could that serve as control for their behavior?
Yep, yeah, we have, I'd say we've got a pretty good spectrum. 3 of the lakes experienced pretty good squeezes, and 3 of the others sort of less squeezed to like pretty buffered.
Thank you.
Anything else? Oh, yes, sorry.
So this is kind of a 2-part question. How are the hatcheries getting their brood stock for each of the strains? And are there any that have been in a hatchery longer than another one that might potentially impact that?
Yeah, all of these strains, I mean, they're all sort of heritage strains. They've been around for some time, and there's differences in how the hatcheries rear them. We sort of collect them at sort of fingerling stages, and we raise them in our own sort of experimental hatchery facility from there on. But these are all quite old strains. So they're collected, in like the 60s and sort of reared and stocked and continue to be managed since then. Some of them hail from Canadian waters, some from New York, and then there's like some hybrid strains in there as well. But yeah, the strain sort of ancestry and stuff remains an interesting component of this.
All right, one more question if we have it. Yes.
Is there any intent to follow up this study with the susceptibility of those fish that are increasing their foraging activities after squeeze? Their susceptibility to harvest?
Not exactly. We do have like some, so a lot of this work is done in sort of a private facility, so we do have some interesting like angling data to go along with it. I'm assuming that's what you mean by harvest, or
Yeah.
more or less. But so the thing is, though, a lot of the private anglers, that's a pretty hot time of the year. It's not a great time to fish for brook trout in general, so we don't have the best data on that, but we've got maybe some that could be mined.
Okay, we have a 20-minute break now, but we will start back up here at
I like
It was